Hello. This year, the SAS team explored various methods and enhancements to optimize user-centric computer vision model development. We leveraged advanced techniques like synthetic data generation and image augmentation to improve the performance of existing models, and developed an interactive dashboard within SAS Visual Analytics to summarize and explore relevant performance metrics across model iterations. The intelligence community has many computer vision models at their disposal. However, sometimes a new object of interest is identified in the course of a mission or from emerging intelligence that existing models have not yet been trained on thoroughly. Traditionally, in these cases, a highly manual labeling process would need to take place in order to retrain and improve the tagging accuracy of the new object of interest. Our project explores enhancements that can be deployed other than mass labeling, to include incorporating synthetically generated images, training on augmented video frames, adding open source video content, and consolidating information into an easy-to-use dashboard for analysts to review relevant information along model outputs. This presentation will walk through the dashboard developed by SAS and outline points of impact to IC analysts and modeling experts, with a focus on model performance of tagging CCTV objects. The landing page of the SAS dashboard summarizes the video files available to the team and the computer vision models run. We start with 557 frames of raw video images, which were then supplemented with 2,930 frames of synthetically generated images, 309 augmented video images, and 146 open source Street View video frames. For each of the video files, the user can double-click on a source video to see all image frames available. For example, this shows all frames included in this specific video, and a user can toggle between the different frames to explore the source data. The synthetic images account for the majority of the images available, but opening these up and clicking through the individual frames, you can see that these images are fairly small, always in the same location of the frame, and always with the same background. This resulted in our early models that were trained on these images to overfit the detection to only the synthetic cohort and miss many, and sometimes all, real-life CCTV images. This is why we next incorporated augmented video frames, embedding the synthetically generated CCTV images into real-world backgrounds and video frames. We can see these by clicking through the CCTV embed. This did improve performance of the models and increased the number of real-world CCTV objects tagged from our video frames. Back on the original landing page, we also have summary metrics on the models we ran, including model architecture, mean average precision, layer sizes, and overall training time. We ran models both with and without the synthetic and augmented image subsets to track changes in performance. Mean average precision was used to gauge overall object detection capability, but throughout the later dashboard, we'll delve more specifically into object-specific tagging success. One of the most recent YOLO v4 models that incorporates both synthetic and augmented data have the highest mean average precision metric, which is a promising sign that the techniques we employed improve model performance. For each of the models the team ran, this model performance summary page shows relevant information regarding objects tagged alongside the confidence probability, both overall and by video source. One of the first models we ran, a YOLO v3 that ran for 3,600 epochs and included synthetically generated images, at first glance seems to perform very well in tagging CCTV objects. However, this view shows performance of all objects tagged across all video files available, and if you recall from our landing page, the majority of the images are actually the synthetically generated CCTV-only frames. Filtering these CCTV synthetic sources out from the right-hand selector shows a drastic difference in object detection totals. When looking at the real-world video images, this model fails to tag even a single CCTV object. The reason for this is likely model overfitting on too many of the synthetic-only CCTV images, and shows that only supplementing an existing computer vision model with synthetic data may not improve performance on its own. Keeping the filter toggled to exclude CCTV synthetic sources, the user can jump to different models to compare performance model by model. Let's take a deeper look at our most recent YOLO v4 model that incorporated both the synthetic and augmented images. This model tagged a total of 321 CCTV objects with a relatively high average object probability confidence of about 71.5%. On the right-hand side table, you can see the CCTVs were tagged across most of the video files and were not clustered to only one or two specific videos, which is a good sign. Within the class label metrics, the user can also toggle between some of additional views to explore whether the model tags match the label information. The IOU Labels tab breaks the total number of objects tagged based on whether they do or do not match the corresponding label that overlap with the model object's bounding box. For this model, only 18 CCTV objects did not match the corresponding labels, and of these, the object probability is very low, at less than 5%. The next question we wanted to answer was, if the model object does not match the label, what were the corresponding mismatched object types? This can be answered with the next tab, where the model class category is on the y-axis and the label category is along the x. From this heat map view, we can see that there is a high frequency of labeled transportation objects being tagged by this model as miscellaneous text. We'll dig deeper into some of these misclassifications further in the demonstration. Since our project is focused on model performance of a specific object of interest across different models, the next page takes a more macro view of tagged objects per model. Along the top, the user can select objects of interest. In our case, we'll filter the page to CCTV. The left-hand bar chart shows the number of this specific object tagged per model, and each of these model counts can be compared to the count of CCTV objects labeled in our LAS labels source, shown in orange along the top. Similar to the previous tab, let's also filter the results to exclude CCTV synthetic sources. Before the filter was applied, we saw the most CCTV objects were being tagged by the first two models, along with the recent all and no sin YOLO v4 models. But once we look at the non-synthetic corpus of video files, some of the v3 earlier models drop off completely, and the models that incorporate the augmented embedded images advance to the forefront. However, just because a model tagged a CCTV object does not mean that it is necessarily correct. Toggling the left visualization to the IOU class match to labels view shows whether the model tagged objects match the labeled classification. One of the earlier YOLO v3 models jump out with a very high misclassification rate of 90%, meaning that of the 10 CCTV objects the model tagged, only one matched a valid CCTV labeled object. Mean average precision metrics have been generated for each of the models run and can be referenced as additional summary information from this page. These are helpful to see precision versus loss across the model iterations. We can assess each model's learning curve to understand how quickly it starts to learn to detect objects and also assess the quality of the final model. Next, we'll take a more detailed look at the overlaps, matches, and mismatches of model objects versus the labeled information, which we will take as ground truth. We use the intersection over union, or IOU metric, which measures the area of the two bounding boxes' total area divided by the area of their intersection. In general, the higher the IOU, the more precise the object detection. This page was developed to be exploratory in nature, and thus allows the user much flexibility in filtering by model, specific tagged object class, whether or not the object class matches the labels, IOU percentage, and others. Let's take a look at one of our recent leading models, the YOLO v4 model that includes all synthetic and augmented video files. and exclude all synthetic video files from our view. This page renders one object at a time based on the user's selection in the list table, but additional image tags can be shown by double-clicking an object of interest and selecting Page Link to JSON Image Full. This brings up the image with all labeled objects in white and all model-tagged objects in pink. Users can quickly toggle between different models on the same image frame to compare model performance across all objects. Going back to the main IOU tab, we can see that for this November 22 all model, most of the objects tagged by the model appear to match the label classes, 95.7% match. But let's dive into the ones that do not match to see whether we can identify an issue with the model or maybe even the labels themselves. Selecting No from the pie chart along the top filters the list table results to only the mismatched objects. We can click through these objects to see both the label and the model bounding boxes on the right. This can be helpful to analysts to confirm exactly what was tagged and labeled instead of having to jump to another application to open the correct file and model outputs. Some of these mismatches seem similar in nature, such as light pole versus power pole, which both could be classified as infrastructure. Additional object class categories were added to this report page to be able to filter where the class categories do not match. Selecting No in the bottom pie chart further filters the list table results and corresponding images to explore. Most of these appear to be true negatives where the model tagged an object that does not match what the object actually is. However, this one shows a large CCTV object labeled, where the model tagged a vehicle, and upon inspecting the image and bounding boxes themselves, it appears the model is correct. Because labeling can be a highly manual and tedious process, mistakes are bound to happen. So in cases like these, the SAS dashboard can help analysts quickly identify mislabeled objects instead of having to look through every single frame to confirm label veracity. To flag a label for review, a user can double-click on the table and select Add Label Review tag. This kicks off a SAS job in the backend that updates the table with a ToReview tag. While the IOU page explores the overlaps between labels and model-tagged objects, the next section looks at instances where the model tagged an object that did not have any corresponding label with any overlap. These scenarios fall into two general categories: objects that the model tagged erroneously, and objects that were identified correctly and should have been labeled. Along the left-hand side, there is a summary of objects tagged per video source and model object class. We can filter the results for the first video file by selecting it from the bar chart or the drop-down along the top of the page. We can look at an object of interest, such as CCTVs, that were tagged by the models but not labeled. Clicking through these, some are clearly incorrect model tags, but others appear closer to the mark. Even if there really are not CCTVs there, they are quite close, which means the model appears to be performing decently. Similar to the IOU page, users can double-click on any of these objects and see the full image context, tag for review, or remove an existing tag. The Object Location Analysis tab explores the position of object labels to check if any frame location biases may be present. Filtering the data on a specific model or object, such as CCTV, location frequency regions across all video files can be seen in a heat map on the right. Locations have been grouped into zones using concentric circles. The center is Zone 1, and the groupings radiate outwards through Zone 4. We can investigate if a model is excelling or underperforming at locating objects within a certain image zone, and users can dig into individual image frames along the bottom of the page, which shows individual image tag locations. There's a high frequency of CCTV labels in the center area. This is due to the large number of synthetic images where the CCTV was generated in the center of the frame. As we've seen previously, this introduced model overfitting. Findings from object location frequencies can be used to enhance synthetic data by placing the desired object in a location on the image where it is likely to be found in the real world. For more information on our final model performance against a set of new video files, please visit our live presentation at the symposium on December 6th. Thank you.